Hello, everybody, and welcome back to Chapter 2 of our presentation about the Deephaven C++ client. I'm Corey Kosak from Deephaven. I'm here with my colleague, Cristian Ferretti.
Hello.
And hopefully you've all watched Chapter 1 of this video, which was about how to access static data from Deephaven with C++. If you haven't, you might want to go check below for links to the first video. In this chapter, we're going to talk about accessing dynamic data from the C++ client. And what we mean by dynamic data are tables that are changing over time. In Deephaven, sometimes we call these ticking tables. And these can be tables that either kind of just append only, they kind of linearly grow at the end, getting new rows. But they can also be more complicated where those new rows can arrive anywhere, in the front or in the middle, or the data can even kind of modify in place.
A canonical source for something like that, right, could be a Kafka stream. But if you're computing something on top of that, let's say you're doing some kind of aggregation based on some column name. Let's say you have symbols that are trading during the day in the stock market, and you see the number of shares that execute for each symbol. You will expect to see like the symbol name, Microsoft, and then a number, and that number should change, essentially grow, but the rows themselves are going to be the same. So it's not something that is append only, Two cases of ticking, like Corey was explaining.
So to demonstrate this, we are going to create a very simple table. It's similar to the one that we used in the static case, but it's going to be changing once every second. So the difference between the previous example is that this is called a timetable. What I'm going to do is create a timetable that ticks every second, and every second it's going to get a new row where the int value column gets this II value that we talked about last time. It's basically kind of our unique increasing row identifier, and the double value gets a simple calculation based on II. So there you go. And you can see the data is starting to tick in, and this is dynamic, and it's just going to go forever. Now, what we're going to do in our first demo program is access this table. And you'll remember this main menu technology from last time. And we're going to do this in steps. In the first baby step, we're just going to print the full table. Every time the table ticks, we will print the entire value of the new table. The code for this is going to look a little different from last time, because the way you do these things is you access the table here as before, but instead of just printing the table, we're going to subscribe to the table. And this is a new call that we're learning now. When we subscribe to the table, we give it a callback object, which happens to be defined right up here. And that callback object needs to have two methods: what to do when there's a tick and what to do when there's a failure. Let's not worry too much about the failure case, but on the ticking case, what we're going to do is the ticking case gets an update, and in this case, we're just going to take the current table out of that and print it to the O string. And I'm going to run this demo and show you sort of how it currently looks.
Current is the current table as it was in the last tick that showed up in the underlying library that is essentially getting this update from the Deephaven server. So that's the important part to get at this point in terms of what that ticking update object is. There are more things there than Corey is going to explain later, but the current is the latest understanding that we have of what that table is as of now.
Right, that's a great point, and we should probably have provided that as a little background. The job of the C++ library at this point is to stay in sync with the Deephaven server. And so under the covers, the Deephaven server is sending updates and variously communicating with the library so that the library keeps its own kind of cached copy of the table on the server. And as Cristian just said, this current table is basically the view on the latest version of that table. So if we print full table and enter the table name, which is called appending.
But we see how it's essentially growing, right? Because 271, 272, 273, and we see like once per second new rows showing up. So
this little bracketed number on the left is printed for debugging convenience. It basically is the
Deephaven tables are ordered So each row has a position. And given that we have a current version of the table with a given set of rows in a particular order, it's the absolute position of the row in the total table.
So as you might imagine, this table is growing without bound, and if I were processing this table every time just looking at current, that might get untenable. I don't want to look at an ever-growing amount of data, especially when we know that this table is an append-only table. It's only getting new rows at the end. Right? So in the second example, the code is basically the same as the first example, but it uses a different callback, namely this callback print diff class. And what this is designed to do is kind of to look into the details of the update and print out the components if they exist. And the components are going to be, there may be removes, there may or may not be adds, and there may or may not be modifies. But basically, there are table snapshots inside that object for each operation type. So here's how the table looked before we applied the removes. Here's how the table looked after we applied the removes. And here's the set of removed indexes. And in fact, when there are no removes, you can tell that just by doing a simple pointer compare. Like this is a smart pointer whose value will be exactly equal to this if there are no removes. So that's it. These comparisons are pretty cheap. Basically, the structure of this code is, well, if there are some removes, then I just want to print them to the stream. I'm going to take the table before the removes were applied. I'm going to refer to the indexes of the rows that were removed, and I'm going to stream them out. And so likewise, the exact same thing for adds. If adds happened, I'm going to print the contents of the table after the add operation was applied. I'm going to refer to the added rows, and I'm going to print that on my screen. Modifies is kind of an interesting case, and I think we're going to defer that until chapter 3. But basically, when there's a modify, you may be interested in what the old value of the row was and what the new value of the row was. And so that's kind of what this logic is telling you here. So I think with that, we can run this on the same table, which has still been ticking away this whole time, by the way. The table is called appending. The first update it got was the whole table, because you're kind of starting from 0, and you effectively kind of logically get an add of the whole table that brings you current. And then subsequent, you can see that every second we are getting basically one row. You can see it there. And furthermore, once again, we'll go to our Deephaven console and kind of compare. You can see that we're keeping up with the Deephaven console.
To try to contrast the two things that we have seen so far, right? First, we saw the full table being printed on a standard out, and now we are seeing essentially the diffs. But in terms of how the process actually is happening, right? The library is generating these TickingUpdate objects. And from the point of view of you, the person using the library, you create these callbacks where you decide what to do with them. We happen to be doing the printing out to standard output as a way to, illustrate how to use it. And we are extracting from that update object the pieces that we want for the different two examples that we have shown so far, right? So in the first one, we are from the update object taking the current table, which is the full thing. And now in the second example, from the TickingUpdate object, we are looking at the different parts of the update itself, the removes, the adds, or the modifies. But that's kind of like the full picture so far.
All right, that's fabulous. And now, to your point, I'm going to actually create a different table that has slightly more interesting behavior. It's going to have removes and adds. So what I'm going to do is I'm going to create it's going to be the last 10 rows only of the previous table that we've been talking about. And as you can see, this table stays of a fixed size, but rows are kind of logically being deleted off the top and being added on the bottom. And so we can use our exact same program here to see that happen. Because our callback was carefully written here to process all removes, adds, and modifies and print them, we should be able to use the exact same thing on this new table called windowed. Print diffs for the table called windowed. It scrolled by kind of fast, but I don't know if you saw, like before, we got the first update we got was the full table. And then subsequently, every second, we are getting a remove, you can see, of row 0 and an add of row 9. And by the way, those row numbers are kind of physical row numbers. So when the remove of row 0 happens, the other rows are effectively kind of shifted up. And so the new row comes at row 9 at the bottom. In a real application, you're not just printing data, you're of course processing data. And so I thought I would show examples of how you would process data coming back from the server. First, let's come up with kind of a toy application. Let's say I want to compute kind of the running sum of the int value column. I'm going to do it the hard way, and then I'm going to do it the easier way. And the hard way is to take the current value of the table every time it ticks and sum up everything in that column and then print it out. And then, this is foreshadowing. And then I'll say, well, for a running sum, you don't really need to recalculate all the values. You can just update your running sum by, for items that are removed, subtracting that out from your running sum. For items that are added, adding those to your running sum. And for items that are modified, subtract out the old value and add in the new value. I'm going to show sample code for doing that. But first the simple version, which is just adding up all the columns in the table. Again, this code is actually pretty much exactly the same, and all of the action is really happening in the callback. Let's trace through the logic of this code, and then we will have a little bit of a tangent on Deephaven data types. As a C++ programmer, and one that's somebody who's probably familiar with Arrow, you may be familiar with the arrow table type and the arrow array types. And your first question is, why am I not looking at arrow table types and arrow array types? Well, unfortunately, Arrow is very carefully and efficiently designed to map those types to kind of fixed regions of memory in a very efficient way. And like the arrow array types really aren't designed for an underlying data structure that may move around and shift.
It's for static data, essentially, right? I think your example for tail of the last 10 rows is a great one to illustrate that point. We saw in the last callback when it was running, we saw how one row was being added at the end and the row at the top was being deleted. Imagine what will happen in a kind of inefficient implementation of updates that way, right? You will be like shifting around data in memory like crazy, which is something that we certainly do not want to do. We try to be efficient about that. And to be able to handle these updates for those cases, we cannot afford to move blocks of column data in memory, right? So we need some kind of table representation that has a level of indirection for the data. And that means that we cannot use plain vanilla arrow array types and table types.
So that's a great point. And as a matter of fact, our underlying data structure for our columns is this project called Immer for C++. And it uses this kind of functional data structure with kind of an underlying fat tree representation where there's a lot of structural sharing. So you can actually take the snapshot of a column, you can make changes to it, you can take a second snapshot of it, and those two data structures will actually share a large part of their underlying structure. And
TickingUpdate is taking advantage of that, right? So when you have the current, there is also a previous, which was the state of the table before, and those are not two copies of the data. We essentially benefit from the way Immer handles this, so that only the part that changes actually is like new data. Everything else is structurally shared, which is great.
Imagine this table that we were looking at is not 10 rows, but 10 million rows. You do not want to pay the cost of a linear deletion of 10 million rows every time you want to delete a row from the beginning. You have to do better than that. That's why we use these data structures. So our abstraction for a column, kind of think of it as a cousin of arrow array, is what we call a column source. You can see that here. And basically, the column source is an abstract class that refers to some underlying representation that we just told you is Immer. And we try to discourage you from doing element by element access of it. It's much more efficient to do sort of bulk access or range access. So the normal way to pull data out of a column source is to allocate a chunk, a kind of buffer for the destination of the right type, and then to tell the column source, please fill this chunk given this set of indexes that I give you. It's the kind of thing, there's a lot of ceremony there. You're like, oh, I just wanted to access my one value. But on the other hand, it provides a lot of opportunity for the library to kind of fetch data efficiently. And so, as in a lot of bulk APIs, you really want to streamline your operations by kind of setting up what you want to do, doing it, and then analyzing the results. I think given that, this code might make a little more sense. Hi. So this is a little embarrassing. So it turns out after we recorded this video and edited it, we realized that the code we wrote for the ticking callbacks was kind of unnatural. It wasn't the code that you really should write. And so I've decided to just jump in with my alternate personality here with the white shirt and just kind of explain the code the way we should have written it in the first place. So this is the callback. We're getting our ticking update, and in this case, because we're looking at the whole table, we look at the value called current, and we get the column called int value. And because we know what types we're working with, we directly cast that to an int64 column source. Then we ask the table what its row sequence is. Then we prepare a chunk, which is basically like a buffer of some reasonable size, in this case 8K. And then we have this loop. And we use these two operations, take and drop. Take takes up to n elements from the front of the sequence, returning a new row sequence, and drop drops n elements from the front, returning the suffix. And so as we're taking the prefix, we are finding out what the actual size of these rows is. It's going to be some number up to chunk size, but it might be smaller. And then we're going to copy data from the column source into our buffer, and that's accomplished via this fillChunk method. FillChunk takes the row sequence that we care about, the target buffer that we want to store the elements in, and there's this third parameter which has to do with nulls. If we had a chunk of booleans, that would be populated with values that are true or false according to whether the element was null or not. Once that comes back, we have this loop. Data chunk is basically a contiguous range of memory. It's basically, you can treat it like a C-style array. We iterate over it, we are summing the data from it, and we are also kind of as a side effect counting operations. And then we repeat our while loop until rows is exhausted. And now at this point, I'm going to hand the conversation back into main universe, Corey and Cristian, and I will catch up with you one more time in a later interruption.
From the point of view of what we're doing for each value in the column that we care about, right, which is the int value column, we are just keeping that int64 sum in line 197, right? So the important part to understand here is that that code is going to execute for each value in the column, and the indirection there, the right-hand side of that plus equals assignment, is the actual value from that column, right?
Right, and so there is a level of indirection there. The reason we have fillChunk is we are doing a copy from the Immer data structure into a flat array-like data structure, just to make it ultimately easier for you to deal with. You don't have to deal with it, and you don't have to know anything about the underlying data structure. Okay, so given that, let's run this code in.
We have our menu.
And we're going to do appending. We're going to do the full table called appending, actually. And so this is kind of a toy example, but the reason I'm printing cumulative number of ops is because every time it's going through this loop, it's summing up the whole table, and I want to show how that's like a lot of work. And again, foreshadowing, in the diff version that works with deltas, we won't be doing that much work because we'll just be processing the deltas. But here you can see we'll have to use like Euler's formula to Euler's formula to make sure that this is correct. Actually, I think I can do this in Deephaven. This will be like a fun test of Deephaven.
Well, you could define the whole thing in Deephaven too, like on the server side, right? I mean, we're doing it client side as a way to illustrate But from the point of view of the actual operation, it's a little bit artificial, because if you needed this, very likely you will define the table doing the sum, like a derived table of the first table, and then just subscribe to that.
Yeah, it's the hazard of having synthetic examples, is that they're all kind of like dumb. But so just to confirm that the number being calculated is correct, I can say appending. Oh, I think I have to select. Well, it's a view int value sum by nothing, I think is the way I want to do this. So I'm going to pull out the int value column and then basically do a group by nothing, so that it'll basically just have one row, which will be the sum of int value. Please work. Oh yeah, okay. So if the number on the other side is about 2.2 million, then we're probably calculating it correctly. There you go. So let's memorize this number, 2250381. And that should have appeared here somewhere. Yeah, there it is. Okay. All right. So I promised you that in the next demo, we would show how to do that more efficiently. That is going to be sum columns diff. Again, the body of the code looks identical, but it's got a different callback once again. Hi, this is Corey again, alternate universe Corey. Going to explain the code we wish we had written for the diff method. And so basically, when onTick is called, the logic here is we're going to process the removes and subtract them out of our running sum. And then we're going to process the adds, and we're going to add them to a running sum. And so rather than, by contrast to the old approach, rather than working with the whole table, we're just going to look at the diffs. What was removed from the table since last time? What was added to the table since last time? So we call this process deltas with the view of the table before the removes happened, a row sequence indicating what the removed rows were, and this -1 flag, which will be used to indicate whether we're subtracting or adding. In the next step, we're going to take the view of the table after the adds happened. We're going to have a row sequence indicating what the added rows were, and in this case with a +1 parity indicating we're going to add those values into our sum. And that process deltas is right down here, and it's very similar to what we saw before, getting the column, casting to the right type, making a data chunk, and so on. The only difference is that rows was a parameter. It came in from our caller, but the rest of it is the same. We are summing in to a variable called int64sum, and we are counting operations. And when it's done, we print it out as before, and that's it, easy peasy. So with that, I'm going to hand the conversation back to main universe Corey and Cristian. What you can predict will happen is like before. The first update you're going to get is going to be big because it's going to be the whole table, but then every subsequent update is going to be cheap. So you can see my cumulative number of ops is just, it's doing one more op each time, even though it's still hopefully calculating the right answer. So if we go over here, we're at about 2614041, and that should have been, yeah, so that showed up here in my stream here. So my code still works, but it's doing a lot less work because it's only processing deltas at this point.
We happen to know that for the table that you're doing it right now, appending, right, we only have adds. We don't have removes. But the same code should work for the other table that was doing the windowing part, right?
Oh, that's a great point, and it will. So let's try that. Let's go back here. I will make another table called we'll let Deephaven calculate the sum of the windowed table for us. And as a reminder, the windowed table looks like that. It has just these 10 rows. So now if we were to run the same demo over here, demo number 4, using the table called windowed, you can see it got the 10-row table at first, and then for every update, it's just doing 2 operations, which logically represent the row that's deleted, it has to subtract out. The row that's added, it has to add 24075. We flip over here and we see that we do have 24075. Of course, these are all toy examples, but when your table has a million rows and it's changing in all kinds of interesting ways, you will be kind of grateful that you can access sort of just the table that changed rather than having to pick through the whole thing.
Remember that we have the Deephaven console on the server side there, sending the updates for the tables that the client is subscribing to. And then the server has the table. The client needs to be up to date to what the table is. So the client also has the table. something changed here, we need to give you some kind of delta so that the client can apply that delta and get the new version of the table after that one change. And we see that this table is changing once per second. We're getting this 1 per second updates and keeping this song going so that we keep tracking the table that is on the server side. In the way that the C++ client is giving you these updates, you actually get to decide whether you want to look at the whole result, or if your computation is actually better than on the changes, you can look at the actual changes that showed up. The sum was calculated on the client side in the last two examples by brute force on the whole table first, and then Corey showed you just processing adds and deletes, which is not the full general case because we're saving modifies for the next installment. But we happen to know that the table that we're doing this for changing ways that do not have modifies on them, so it works.
I think maybe as a final comment for this video, we should show the fields of this TickingUpdate class because it might be
illustrative.
Basically, these are the public getters for this class, and it might look like there's a lot here, but there's a certain logic to it because it kind of depends on, as Cristian just said, kind of what you care about. If you only cared about how the table looks currently after everything's applied, you can read the current getter. If you somehow cared, well, I want a before and after view, you could look at the prev table and then the current table. And I think it should be stressed, it's very cheap for us to keep multiple snapshots of the table as it evolves over time because of this Immer data structure that we're using. So these tables, although they're sort of logically distinct, they are sharing most of their substructure. If you cared about more detail, as we have in this demo, you can also get data at the granularity of, well, what happened to the remove step? How did the table look before the removes? How did the table look after the removes? And what were the sort of indexes of the removed rows? And that's exactly the same for adds. What did the table look like before and after the adds? And what were the added rows? Modifies work almost the same way. There is just a detail because we tell you about the modified rows on a column by column basis. So for example, we may tell you, well, in column 1, rows 10, 20, and 30 were modified. And in column 2, rows 40, 50, and 60 were modified.
For adds and for removes, essentially, obviously, things are happening for full rows, right? You remove everything in a row. All the columns are impacted. That particular row went away. For adds, same thing. Modifies are different in the sense that they can be sprinkled. Not every element in a row may have changed. So we try to be efficient about telling you just what changed in a more granular manner.
Very cool. And I wanted to add, because I think we probably will get a question from some eagle-eyed viewer. Even in this data structure, there's a little bit of redundancy. For example, you will notice that after removes and before adds actually return precisely the same value. And that's because internally removes are applied first and then adds and then modifies. And so the point after removes and the point before adds is exactly the same point. But that's not a typo. That's just because from the user's point of view, it makes it a little cleaner to be explicit about it.
There is a song and dance there where Deephaven is trying to give you, these are the particular rows where something happened, and then you can go and say, okay, give me the values for this column or that column or that column. So that's trying to explain what we have these, like, 2 steps, and why we're talking in terms of which particular rows with the row sequences.
Yeah, that's a great point, and we should remind people it's always more annoying to program in bulk, but the efficiency gains are worth it. So that is why, if you're going to go to the store for a carton of milk, you might as well go and get a carton of milk and eggs and bread. It's just the usual batching argument.
So in our coming one, we promise you that we'll unveil the modifies, right? So in the next chapter, we will show you a table that also has modifies. You probably can kind of, like, from what you have seen so far, you can kind of tell how that story will go, but you will see.
All right. Well, great. thank you for all for watching this. Stay tuned for chapter 3.
Coming soon.
We'll see you next time.
Ta-ta.